Hi everyone. In this video I would like to show you how I integrated genetic algorithms with Topologicpy. Obviously this is not a new thing. Many pieces of software, especially in Grasshopper and in Dynamo, have worked with genetic algorithms. But Topologicpy has not really worked with genetic algorithms so far, so I thought it would be nice to include this kind of demo, and I am sharing it also with my computational methods and architecture students. So for this example, I tried to do something very simple that would run in a reasonable amount of time. As if you have worked with genetic algorithms, you probably already know that they do take a long time to converge on a solution. In this example, what I did is I imagined that we have a site with some kind of buildings around, and we are trying to decide how to locate a building and orient it so that it satisfies two conditions. Basically, these are the two objectives we're going to satisfy. We would like it to be facing as much as possible south, the south direction, which is in this case would be pointing towards the bottom of the screen. As well as to maximize the views, so it will have to kind of have views between the buildings in order to maximize them. So the way I set it up is that if it is facing completely south, the view is blocked quite a bit of degree. But if it moves towards, let's say, the east, if it rotates towards the east, the views open up because there is like more buildings, more openings between the buildings, over here. And of course, towards the west, it's also blocked quite a bit, etc. Now, I have limited what this facade can do in terms of where it can go. Obviously, we don't want it to intersect with any of the buildings. So the range is limited to this area in the middle, and the angles are limited from, let's say, minus 90 from the south to plus 90 from the south. So let me just go through all of this. Before I start also, I wanted you to know that I'm using a library called pygad, P-Y-G-A-D, which is an open source Python library for genetic algorithms. It is really quite powerful. It has a lot of options. I just started learning it, so I'm not familiar with all its intricacies, but I'm using some tutorials and some standard methods in it to kind of integrate it with Topologicpy. Also, this genetic algorithm is not actually inside the Topologicpy API. It sits outside, so you have to import the library and work with it, but you can then connect Topologicpy to it. Okay, so let's start from the beginning. So basically, and let me move this stuff a little bit over here. The first cell always is to import all the Topologicpy libraries, and we are going to now set up the environment, basically the site and the buildings. So basically I'm specifying here the origins of these buildings, and then I'm making a rectangle for the ground, a grid basically, a shell.rectangle, and then 5 buildings as you saw in the image. These are simple prisms. This is really a 2D problem that I'm setting up here. So I made all the heights equals to 10. So basically I'm just simply shooting the rays in 2D. And then these are just simply corners, 8 corners. You'll see them later on. This is just simply to bracket the scene, because I want to do an animation and I don't want it to jitter. So I'm making like almost like a bounding box, a set of 8 small dots that are surrounding the context, the buildings. So I create a cluster by topologies, and I call it context, and I return that context. So this is basically a function called create context that returns a cluster. So now I call it, just to kind of do a visual check, I say context equals create context and topology.show this context, and I set the camera, and we can find out what it is doing. So here it is. This is the context. As you can see, you see those 8 dots that kind of bound this site, and the 5 buildings, and it's ready to go. So all we need to do now is set up that facade or face and then kind of shoot rays from it. So how do we do this? So the next step is to set up the building facade. So basically what I'm doing here is I have a function that says create face, and it takes an x and a y for the x and y location and an angle of rotation from the south. So I create the origin of this face. I create a rectangle that starts out sitting on the ground horizontal, and it has this origin V, and it's a 10 by 10 rectangle, let's say 10 meters by 10 meters, whatever you want, 10 units. And then what I do is I stand it up on its edge, so I rotate it around the x-axis by 90 degrees, so now it's standing up. But as you can imagine, if it's standing up and it's rotated around a vertex that is sitting on the ground, half of it will be buried into the ground. So I translate it or move it up in the Z half its height. So I move it up by 5 so that it is sitting onto the ground. After that, I rotate it one more time, this time around the Z axis by the supplied angle here, so that it is now pointing in the correct direction. So this is creating the face, and it returns the face called f. The next function is to create the rays that are emanating from that face, as you can see perhaps here. These are the rays that are going to emanate. I decided to emanate only 7 rays and check which ones are intersecting the buildings. So to create the rays, I get the centroid of the face. So I get supplied with the face here. I get the centroid of it. I get the normal, which is a line that is perpendicular to the face. And then I set up an empty list for my rays, and I go from -30 to 40 in 10-degree angle. So basically from -30 to 30. And I append the created line that I rotated, and I append it to the list of rays. So I take n, which is the normal, with origin C. I then rotate it by an angle here, I, and then I append it to the list of rays. So I get 7 rays when I run this function. The last function is to actually now calculate the number of views. And the way I calculate the number of views, which kind of gives me a bit of a score about whether from this location, from this vantage point, do I see like far or not. So basically I give the 7 rays to this function. I create the context again. I could have like maybe cached this, but I was a bit lazy here. So I'm basically recreating the context. And then I initialize the number of rays, number of views into 0. And then I go through the rays and I find out whether they have intersected any of the buildings. The way I am doing it here, and there are a couple of ways you can do it, but the way I decided to do it is to subtract the ray from the context. So just simply edge minus cluster. And if the instance of the result is a topologic edge, because obviously if it intersects it and you subtract it, you might get a cluster of kind of parts of the edge, right? This continuous part of the edge. So if it is an edge, then I look at the length of this edge, that was the result, and if the length is equal to the ray, that means it did not intersect anything, it stayed as is. And if that is the case, I add 1 to n, and then after I've gone through all of them, I return n. So if we look at the diagram here, you can imagine, for example, this ray here minus the buildings is the same ray, so that gets added. This one here will be a cluster because this part here in the middle of the building will go away, so we'll get a cluster of 2 edges. That will be a cluster, so nothing is added. This will be a cluster as well. This will be a cluster as well. This looks like it might have survived here, this one, so that survives as is. And these last 2 also get cut up and they are not added. So you can see here that the number of views is 2, which is exactly what we have. We have this ray over here and this ray over here. So basically, I'm just exercising this again in order for me to see it. I'm setting the angle to be 45. I'm setting x and y to be 40 and 30. Sorry, the angle is minus 45. This is the length of the ray. And I'm calculating the number of views. I'm printing them out and I'm showing this. So let's just simply change it to minus 90 here. Sorry, to 0, so that it's pointing south, and let's see what we get. It will take a little bit of time because it's going to intersect them with the 5 buildings, and then it will give us the result. So in this case, the number of views is only 1, and this is the visual result of it. So let's kind of investigate it a little bit from the top here. So you'll notice this ray is intersecting, this one is free, so that counts as 1. This is intersecting, this is intersecting, that's intersecting, that's intersecting, and that is intersecting. So it's only one view that survives. So that's kind of how I set up the problem. Now if I move it to 45, let's take a look at 45 and what happens there. Of course, only from this location, but I could perhaps move the x as well. Let's say to 50, and move the y to 20, maybe to 20, let's say. And let's try that. I don't remember what the numbers would be, but we can test them and see if the situation improves. Obviously, the more we move from the south, the worse the score is going to be for the genetic algorithm. So in this case, as you can see, not a great location and great angle, because again, we moved from the south and only 2 views are there. So at least if we move, let's say 1 over, we might get more rays. So let's just go ahead and do that one more time. So move it to 60 and try it one more time. And see how many number of views we get. So now we got 5 views, which is great. So this is a good solution, but obviously it has moved 45 degrees from the south, which is not ideal. So the idea is we do this setup. We give these numbers to pygad, to the genetic algorithm, and we see whether it can find for us a solution. So how do we do this? We import pygad. We do need numpy as np. This is for just some arrays and stuff that I'm doing. I'm printing the version because just for debugging, I was facing some issues with pygad and I wanted to know which version it is. And I'm preparing empty lists for all the solutions after every generation. So I'm preparing a list of the x positions, a list of the y positions, a list of the angles, and I have 2 fitnesses, basically the fitness for the orientation and the fitness for the number of views. So the first thing and the most important thing is to define a fitness function that the genetic algorithm will call. So let's go ahead and take a look at that in some detail. It will you have to put these as inputs. Basically, this is what the genetic algorithm will give to this function when it calls it back. It will give it an instance of the genetic algorithm. It will give it the solution and a solution ID. Okay. So basically, the solution will contain your inputs. So you will have the x, the y, and the angle. So you can build your face and the rays from that and calculate what happens, and then you can calculate the fitness of that solution. So the angle from the south, I decided to make it the absolute of that angle just for the calculations, because it doesn't matter if it is turning towards the east or the west. The more it turns from the south, it gets a worse score. So now we do the same thing. We create the face based on the x, the y, and the angle. We create the rays based on that face, and I am doing the length of the rays to be 100 so that they're long enough to intersect the buildings, because I don't know exactly where that face is going to end up. So I just wanted to make sure I have a long enough number of rays that will intersect the buildings. And then I calculate the number of views by calling that same function number of views, and I give it the 7 rays. Now, Because I have limited it to limited the x between 20 and 60 and the y between 20 and 40 and the angle between minus 90 and 90, any numbers that are outside those ranges get a score of 0, so a fitness of 0. So that's the worst fitness. The worst fitness is 0 and the best fitness in my case is 1. And you should know that pygad always attempts to maximize the fitness. So if you have something that needs to be minimized, you need to change the logic of the fitness so that it is being maximized. So fitness 1, which is the angle from the south, is basically 90 minus angle from the south, which is the absolute of the angle, so that's a positive number, divided by 90, which gives you a ratio from 0 to 1. So if the angle is actually 90, 90 minus 90 is 0, 0 divided by 90 is 0. So that is the worst angle. That means it's facing either east or west. And if it is facing south, that angle will be 0. So 90 minus 0 will be 90. 90 divided by 90 is 1, so that is the maximum fitness that you can get. In terms of the number of views, we know that the maximum number of views is 7, so 7 divided by or the number of views divided by 7 gives you the ratio. Of course, if 7 of them have survived, you will get a fitness value of 1, which is the maximum. And because we are returning a list of 2 fitnesses, pygad automatically understands that this is now a multi-objective optimization, MOO, and it will try to optimize on both those dimensions, fitness 1 and fitness 2. Another callback function is on generate. So basically when one generation is ready and the best solution has been found in that generation, you can define a function to capture that information. So basically it gives you the GA instance, which you can call to get the best solution from that GA instance, the best solution for that generation. That gives you the solution fitness, and the ID of that solution. So the solution gets translated into X, Y, and angle. And then what we do is, again, we create the face, we create the rays, we create the number of views, or we calculate the number of views. We print them out so that we can see them, but I capture them at that point. I append them to the X list, Y list, and angle list here. And also the 2 fitnesses from the solution fitness, which is this coming in for the angle and for the number of views. I capture that fitness and save it as well. And then now we want to actually create the constraints for the problem. So we're creating a gene space. What does that mean? A gene space is basically the allowed values for every gene. So the allowed X positions, as I said before, are from 20 to 60 in increments of 5. The allowed Y positions are from 20 to 40 in increments of 5. So I'm limiting what numbers, and it will speed up the genetic algorithm because it will not be continuous numbers. It will choose one from that list. And then the allowed angles is from minus 90 to plus 90 in increments of 10. And then some hyperparameters for the genetic algorithm, or parameters for the genetic algorithm. I'm limiting the number of generations only to 10 generations. The numbers of pairs that will be mated is 10, so all of them will be mated because actually the solution per population is 10. And then the number of genes is 3 because I have X, Y, and angle, so the number of genes is 3. And this is where you have to look up the API and find out how do they do parent selection type. There are different strategies for parent selection, different strategies for the crossover and the mutation. I chose single point and random. And the number of genes that will be mutated, in this case 50%. So basically either one, probably 1 out of the 3 because it's a very small number. So 50% of 3, 1.5, I don't know if it will go to 2 or to 1. But only a part of them will be mutated. And then I create an initial population. So, but basically what this is why I need NumPy. I'm creating a matrix based on integers, and I'm using kind of numbers that are sampled from this gene space. So I'm saying, fill a matrix with numbers between 20 and 65, and the shape of it is basically the solutions per population, which is 10. So it's going to be 10 by 3. So the number of genes is the columns basically. And just fill out some initial numbers. It really doesn't matter because it will change them immediately once it gets a fitness function, and it will do its job there. The next step is to create the actual genetic algorithm class. So GA instance is pygad.ga, and you give it all the parameters that we just specified right here. And then we ask it to run. I'm not going to run it now because, as I said, it takes a long time. And we get the best solution once it finishes, and from GA instance.best solution, and that's where we are. So this is from the previous run, as you can see here. It gives a warning about this time delay, user warning. I don't know why. It's inside pygad itself. As you can see here, it's in pygad.py 1139. Something has been deprecated, but I don't know why. It doesn't affect anything. I put something on their GitHub asking about it. We'll see what happens. So these are the 10 generations, as you can see here. The first number here, you can ignore the first column because that's just the index of the solution from the population, not the number of generation, but the index of the solution. But this is the X, this is the Y, this is the angle, and then this is the number of views that was calculated, and then the first fitness and the second fitness. So you can imagine if the angle is 90, that means it's facing, let's say, east, it has a fitness of 0. That's not very good. But because we have 5 out of the 7, we get 0.714. And so on and so forth. It goes through 10 iterations, and it finds the fitnesses, and then at the very end, it finds the best solution. In this case, X is 25, Y is 40, the angle is 0, so it's facing south, which is good. 2 views, and then we get a 1 and a 0.2 as the 2 fitness functions. After that, basically, I have the X list and the Y list and the angle list, so I can go through them. They have been cached. Let me just show you that for a second. Here, and I go through that list. I get them. I get the rays. I again create the face based on those numbers, the number of rays. I don't need to calculate the number of views, so I can save a little bit of time here. But I calculate the fitness as the average of those 2 numbers, the 2 fitness numbers, and then I create a color by that fitness value to color the face. So data 01 is the face. It has a face opacity of 1, and the face color is color, which is a plotly color calculated from the fitness. And then I bring in everything else, all the other topologies, make plotly data out of them. I create a plotly figure with a white background. I set the camera for it, and then I save it to a PNG file with the correct number. So you get that. And after that, you'll see I upload it to an online website that creates animated GIFs, and I can show you that in a second. So here it is. So these are the 10 solutions that it found. And you can see that the color gets warmer because I'm using the thermal color scale as it kind of goes more towards the south and the number of views increases. It's obviously not the I don't think it found the optimal solution, but because I only have 10 generations, because I'm using this only as an example, if I let it run for longer, and if I allowed it to move in smaller increments, it probably would have found a very good optimal solution. I hope you enjoyed this video. I know it's a little bit more involved, but this is what it takes with using Python and genetic algorithms and Topologicpy to get this kind of exercise going. Thanks again for watching.